Hi everyone, and welcome to the AI Research Roundup. I'm your host Alex, and today we're diving into some fascinating work on making large language models more efficient. The paper we're looking at is titled 70% Size, 100% Accuracy, Lossless LLM Compression for Efficient GPU Inference via Dynamic Length Float. Essentially, it introduces a new technique called dfloat11 that shrinks LLMs by about 30%, completely losslessly. That means the outputs are bit for bit identical to the original model, which is pretty amazing for deployment on hardware with limited memory. Okay, so this first table really drives home the practical impact of that 30% saving we just mentioned. It compares running different large models, like Llama 3.1405B and QN 2.5, using the standard bfloat16 format versus this new dfloat11. You can see the required memory for dfloat11 is much lower, consistently around that 70% mark we discussed. And crucially, look at the successfully run column. For every model shown, the bfloat16 version failed on the listed GPU setup because it needed too much memory, while the dfloat11 version ran successfully. This really shows how dfloat11 lets you fit these huge models onto hardware that just couldn't handle them before. Okay, so how does dfloat11 actually achieve this saving without losing information? Well, this figure really gets to the heart of it. On the left, you see the standard bfloat16 format that models typically use. It has 1 bit for the sign, 8 bits for the exponent, and 7 bits for the fractional part, or mantissa. Now, the interesting part is on the right. These charts show the actual information content, the entropy, for each of those parts across several big models. Notice how the sign and mantissa entropy bars are almost full, meaning those bits are pretty efficiently used. But look at the exponent chart in the middle. Even though it gets 8 bits, the actual information entropy is way lower, only around 2.6 bits. That means there's a lot of redundancy, about 5.4 bits worth, that can be compressed. And that's exactly what dfloat11 targets to get that space saving. Okay, so building on that idea of the exponent having low information content, this figure shows exactly how dfloat11 takes advantage of it. On the left, you see the dfloat11 format itself. Notice the sign and mantissa bits. They're kept exactly the same as in bfloat16, fixed width, no information lost there. But look at the encoded exponent part above them. Instead of a fixed 8 bits, it uses dynamic bit widths. This is achieved using Huffman coding, illustrated by the tree on the right. Basically, exponent values that appear more often in the model get assigned shorter bit codes, like 0 for exponent 119, while less frequent ones get longer codes. This variable length encoding brings the average bits needed for the exponent down to that approximately 2.6-bit entropy level we saw earlier, resulting in the overall compression. Right, so we just saw how dfloat11 uses Huffman coding to compress the exponent part of the weights. Now, this table is really important because it answers the key question. Does this compression mess with the model's performance? It compares accuracy and perplexity, which are standard ways to measure how good a model is, for the original bfloat16 models and the compressed dfloat11 versions. And, well, you can see the numbers here for Llama 3.1 and QN 2.5 across different tests like MMLU and Truthful QA. They are absolutely identical. Same accuracy, same perplexity. This confirms that the compression really is lossless. It doesn't change the model's outputs 1 bit. Okay, so building on that confirmation of lossless performance, this table gives us the hard numbers on the actual compression. dfloat11 achieves across a whole bunch of different models, from smaller ones up to that huge Llama 3.1405 billion parameter model. You can see the original size in gigabytes, and then the size after dfloat11 compression. The key columns are the compression ratio, which is consistently right around that 70% mark we've been talking about, and the compressed bit width. Notice how that bit width is always hovering around 11, usually between, say, 10.8 and 11.5 bits, which makes sense given the name dfloat11. So yeah, this really quantifies that roughly 30% lossless saving across the board. So that 30% memory saving we saw isn't just theoretical. This figure really shows what that means in practice during model decoding. We're looking at GPU memory usage on the y-axis, as more tokens are decoded on the x-axis. The red line is the original bfloat 16 model, and the blue line is the compressed dfloat 11 version. You can clearly see the blue line stays much lower, representing that memory saving. And the big payoff is that because dfloat 11 uses less memory for the model weights, there's more space left for the KV cache. This lets the model handle significantly more tokens. Look how much further the blue line goes before hitting the out-of-memory point compared to the original model. This translates directly to supporting much longer context lengths during inference. Okay, so that extra memory for the KV cache is great for longer sequences. But what about the actual speed? The throughput and latency during decoding? Well, this figure tackles exactly that. It compares the performance of the original bfloat 16 models, shown in red, which often have to offload parts to the CPU because they don't fit on the GPU, against the dfloat 11 compressed models in blue, which run entirely on the GPU. Across the board, for different models and batch sizes, you see the blue bars are higher for throughput on top, meaning more tokens per second, and lower for latency on the bottom, meaning less time per token. So dfloat 11 isn't just saving memory. It's actually leading to faster inference compared to having to offload the larger original models. So yeah, it's pretty clear that dfloat 11 offers a significant advantage. You get that huge memory saving, around 70% smaller, and faster inference speeds, all without losing any accuracy. This kind of lossless compression is really important. It makes deploying these massive language models much more feasible on the hardware many people already have. It's a big step for more efficient AI. Well, that's all the time we have for this week's AI Research Roundup. Thanks so much for tuning in. I'm your host, Alex.